So, good morning. We are back to consideration of the integration theory. Welcome to Krishna's classroom. And in this lecture, what we work out is the the strategy to modify Riemann integral and the challenges it poses, and eventually check whether it becomes something very satisfactory to us or not. Not all these things we are going to do in this lecture, but certainly work out a path. And in course of these lectures, sometime or other, we will eventually see that our objective is fulfilled. Okay, let us recall the Riemann integration. I am going to do the definition of it. So we talk about compact intervals A, B, R. Then we talk about what are called bounded functions. On AB, and then we define what are called the Riemann integrable functions. RAB, a class of Riemann integrable functions. Then, of course, we wanted to possibly do analysis on this class of functions. We found RAB is a linear space. That is fine. And one can introduce a metric on this space. By DFG, we define through the integral, the new integration theory that we have developed, through the integral A to B f minus g dx, or one can and we have already seen that if f and g are Riemann integrable, then mod f minus g is also Riemann integrable. Or in short, it is amounts to saying that if f is Riemann integrable, then mod f is Riemann integrable. Therefore, this integral is well defined as a Riemann integral. And then one can show that DFG essentially fails to meet the requirement that it is a metric, because DFG is a pseudo. Why it is a pseudo metric? This is because DFG equal to 0 does not imply F equal. So we went through some modifications on this, and we introduced that F. We said that F is equivalent to G if DFG equal to 0. This is a relation. F is related to G. Now this is to be read as and we define a relation on RAB. And this relation is an equivalence relation. It partitions RAB into equivalence classes. And we denoted this collection of equivalence classes we denoted by R bar AB. And this, of course, you can write R AB. And with that is the classes to which F belongs to, the class to which G belongs to, defining D tilde I simply write D FG R tilde AB with D tilde is a metric space. So we could construct a metric space out of it. Which this is no more a pseudo metric, but it's a metric. Therefore, it's a metric space. So you can do analysis on that. Okay. So R tilde AB is also a linear space, and D tilde is a metric on that. Therefore, you have metric space. Then we found that R tilde AB is not complete. Now, this was a disappointing thing. That means with all sorts of hopes, the metric space we constructed using Riemann integral fails to be a complete metric space. The problem with the complete metric spaces, incomplete metric spaces, is that if you take any Cauchy sequence of elements in that space, you cannot assure that it converges to an element in the space. Therefore, working or doing analysis on these kind of spaces is not a comfortable thing to do. Okay? So this is a major drawback. major problem which calls for bringing in new functions into the integrable class and possibly getting a completion. So essentially the question that you ask is what is the completion of R tilde AB? That means some additional functions are also to be amenable to our integration theory. So what is the completion of? So the question is this is the question that you are asking. So you clearly see that we have completely extracted out of whatever you can do with the Riemann integrable functions, which worked under so many constraints. So we have to get rid of some of these constraints and enlarge the scope of integration theory. So a new integration theory which can accommodate a larger class of functions is called for. At the same time, the new integration theory that we develop has to be a generalization of Riemann integration. That is, if f belongs to RAB, then I of f should be equal to integral a to b, whereas this is the Riemann integration. I f denotes the new integral. This is what you mean by it's an extension of the existing Riemann integration theory, so that on all Riemann integrable functions, the new integral should conform to the Riemann integration. Okay? Therefore, we essentially go beyond and get a larger class. This is, let me call larger class, and it accommodates all this, and this larger class is a complete metric space with a generalization of the metric that you have defined on Ra. That's the whole strategy. That is what we want to do. So re-engineer. So what is required is re-engineering the integration theory. Get to the drawing board. Get to the drawing board again. And re-engineer the integration. So that's our main task. Okay, let us make our task less complicated. So what are the drawbacks here? The drawbacks are it is applicable only to a limited class of functions, namely bounded functions on the on a compact interval. That's a handicap. Okay. So what do we expect the new work lead to? Okay. So let us write down what do we expect. One, we would like the integration concept to be applicable to a larger class of functions. Namely, that our new theory class of functions. Other class of functions. Not necessarily bounded. So that's the first one of the things that we want to get rid of. Secondly, it could make on the infinite intervals also. It is not the case. Okay, so that's what you mean by a larger class of functions. On every it should coincide with Riemann integration. For the resulting class integrable functions should be complete in the sense that all Cauchy sequences should converge within space itself. With respect to the modified image. So let us see what are the problems. You see that if you re-examine the Riemann integration, there you see that it is essential to have the functions bounded. Okay, because while defining the upper integral and lower integral, we use the fact that f is bounded, and also the compact integral. Okay? Right? So that was a problem. And of course, we'll work out how it works on, because in the definition itself will not make the distinction between a bounded interval or a compact interval or a non-compact interval. So that is something that we can do possibly. And having done that, it should check with the Riemann integration or coincide with the Riemann integration for all Riemann integration functions, so that what we obtain or what we construct through this process will be a genuine extension of the Riemann integration and eventually the completeness. Because this is something which cannot be verified. But let us try to work out this strategy. So certainly it is clear that you would have a possibly different strategy to define the integral. We should have, we should in a way coincide with the functions which are Riemann integral. So let us see how do we get on to this. But before we go further, we'll simplify our task slightly. Because you know that for functions in R, we had the Riemann integral could be defined for non-negative functions and then get into the get it to and get it defined for the an arbitrary f in an array. Okay. Recall that for every f belonging to AB, the Riemann integral a to b where both f plus and f minus are non-negative. Non-negative functions and of course f plus is defined as maximum, or you can write supremum of zero b and f minus defined as so that f x is equal to and mod and then we could prove that f plus and f minus are both Riemann integrable, and this result was true. So that was the strategy. In fact, the A graph of this would make things clear. Suppose you have a function like this. Suppose f is like that. Then you see that f plus is this one. This is your f. And the f minus is essentially okay. I made a mistake here. I just correct it. Minus of minus of infimum. The f minus is what you do is you take the reflection of this. Okay. So the function is going to be the f minus is going to be this. So this is your f minus. Okay. So what you do is you take the minimum of f and 0 or the infimum of f and 0 is given by this, this and this, and then you take minus of that. So that's the case. So you have f plus and f minus. So you have f is equal to and further integral of f equal to integral of f plus minus integral of f minus. Therefore, it is enough to develop the theory for non-negative Riemann integrable functions in this case. Okay. So we will use the same strategy. Okay. So functions in the new class we will break up into when this does not require any condition that it is Riemann integrable. Therefore, you can break it up into f is equal to f plus minus f minus. Okay. Therefore, our strategy is to work on what are called non-negative functions. So we work on non-negative functions. Okay, so that from that you can combine these two. I'll come back to this. What kind of problems you will encounter. Okay, we are not assuming anymore that our function f is bounded. Therefore, even f plus and f minus are not bounded. Not assumed to be bounded. F plus and f minus are also not bounded, not necessarily permutation. Okay. So henceforth we shall assume that we work on. Okay, we henceforth we assume that f is greater than or equal to 0 and defined on the entire R or any subintervals of so that's the first uh, you know departure from the conditions that we have introduced for Riemann. So a larger class of functions is now under consideration. Okay, and we have already given the strategy that for an arbitrary function, how do we work on this? Okay, I'll come back to that point. There are some tricky points that come here, and possibly for such functions, the integral that we define may be infinite. Okay, this is one problem, right? Therefore, you expect a problem to crop up here. That is, we have to talk about infinity minus infinity. And what do we mean by that? Or is there some way in which we can take care of these kind of issues? Okay, so we'll come to that. I'll explain it out later. So we are assuming, so f is assumed to be some interval, okay, or rather r f is greater than or equal to 0 and rather this f is a extended real valued function. So we will take this as r union plus infinity minus infinity. So this we give a name. Should write this as r star. So r star, let r star be the extended real line. Real line includes, which includes plus infinity and minus infinity. So we are talking about what are called extended real valued function defined on subsets of R. Okay. Now you see that. Let us see what did we do in the case of Riemann integration. In the case of Riemann integration, we had bounded functions, of course, on bounded intervals. We had what is called the upper integral and the lower integral defined. And then, of course, the upper integral, if the upper integral is equal to the lower integral, then you said f is Riemann integral. This was our strategy. Can all these upper integral, lower integral be really made use of the fact that f is bounded and you are working on a compact? Okay, so let us now see what we can do in the new scenario. So for Riemann integrable functions, we had the upper integral and lower integral. So essentially, we approximated the given f from above, from below, and above by step functions, or what you call simple functions. Subordinate to a partition so what we had was this. You had this interval AB. We partition this into x0, x1, xn, and I'm choosing to draw a function whose graph is non-negative. It is immaterial in this case, but as I said, we will consider only non-negative functions. Okay, so what do we have on each of these intervals? Neutralize. Make certain things clear. So you had this is f. We have taken f to be non-negative, and we had c. This height, you had taken this as xi sub star, and the point where it attains the maximum or supremum as xi star. These 2 points are xi sub star and xi star. So we had on minimum value on xi and xi star is where f takes the maximum value and there may be more points where this could happen. Okay, and we had mi star mi equal to defined as f of and mi xi star. Then what do we have? See, we were approximating this piece of the function. This piece of the function we had been approximating in 2 ways. One, of course, by this one, by this path, and on this portion, we were approximating by the function to be taken as capital Mi. So this is your small mi, and this, of course, is the is the this is small capital Mi and this is small m. Likewise on all intervals, because we have introduced a partition. The partition is given by partition P is given by K equal to x naught x1 less than xn equal to b. This is the partition. So corresponding to this partition, for the given function you had something defined. So what do we have? We have a two-step functions. So the step functions that we had was this. So we had two step functions. S, we write here S x defined as sigma mi into characteristic function of x and Sx defined as sigma and this is for I equal to 1 to n minus 1 plus m n it's a well defined function. Now this is for x belonging to a. So you have two functions, two step functions, small x and capital S. Sorry, small s and capital S. And you had this relation, namely that then of course you had what you call the area enclosed between Sx, small sx, the ordinates at x equal to a and x equal to b, and the x-axis. So you had this relation that is equal to which is the Riemann integral, which is less than or equal to integral a to b, that is the area enclosed. Okay, so the integral is actually, the Riemann integral is actually squeezed between the integrals of two step functions, one approximating it from above and the other one approximating it from below. Okay. Now what happens is when you refine this partition, then you see that you will have a monotonically increasing set of lower approximations by step functions and monotonically decreasing sequence of uh, step functions which approximate. Okay, and there will be the corresponding integrals that you have for those functions. I mean, they are well defined, but this of course is something hypothetical. We don't know. Then we had said that the supremum of the lower integrals is what you call the lower integral of a to b. So you see that integral a to b what you call by taking what is called the supremum. And then similarly, by taking the infimum of upper integrals, you have integral a to b You can write this as this is fx. It actually goes down because it is bounded above and it's a decreasing sequence. Integral A to B. Now these two upper integral and lower integral exist. If they are equal, then you said the function is Riemann integral. Otherwise, no. This was our strategy. Okay? So we don't know whether it is happening. If it is happening, then you said it is Riemann. Otherwise, it is not. Okay? So you see, this strategy as such does not work because we are now, because it really depends on our assumption that the function is bounded. Okay? All these, the supremum of the lower integrals, lower sum, and the infimum of the upper sum exists, makes use of the fact that f is bounded. Therefore, one of the modifications that you will have to do is, if you are to accommodate functions which are not bounded, you are taking only non-negative functions for the time being. Even if you are taking the non-negative functions and we are not assuming the function is bounded on the interval, then you see you will have to really forego. I mean, I still work on a compact interval. Okay, I'm just trying to find out some of the difficulties. So when you still work on this, you can approximate from below by these kind of functions. But from above, you see, if the function is assumed to be unbounded, that means at some points the function is likely to take the value infinity. Then you see that the upper integral will create problems because the upper integral is not properly defined. It may be infinite. Okay? Right? So there is no upper approximation that we do, but only the lower approximation. So we'll work with bounded step functions which approximates to the function from below. Okay? So that for each of those functions, the integral is defined, and of course, we examine the limit of that because it's an increasing sequence of functions which approximate from below. They are all bounded functions, and you know that the the area enclosed between that curve and that is the step function curve and the coordinates and the x-axis is well defined, and you will be looking at, of course, one thing that you cannot say is that this is going to be bounded. You cannot say that anymore. So we will be examining this. Anyway, there is no scope for working with the infinite, the upper approximation, because if at some point the function is unbounded, you keep getting this sum to be infinite all the time. Okay, that is one way in which we can forego about the thought of approximating from above. That is what I wanted to say. So let us forget about that. So we shall consider only step functions which approximates the function, the given function from below. The reason is the integral of an upper approximation is maybe for every such if f is lower. But lower approximation, yes, we can build a lower approximation which is a bounded approximation. So that is the first point. Still, we may not reach out to the whole thing. Therefore, this suggests another point. The other point that we work out will open up a lot of possibilities and probably give us a lot of leverage to get more functions into the class. But it will add to all sorts of problems. Okay. So what we do is, with this in mind, we are now considering functions which are non-negative. Yeah, on the interval, on some interval A, say, we keep this. We can take the special case where it is. Okay. So what we do is, you recall the Riemann integral, we were somewhat rigid about our strategy. Namely, we introduce a partition on the interval AB, irrespective of what function we are going to work with. So the function has no role in the partition of the interval AB. Okay? So that is one, probably nice thing about the Riemann integration, but also that is a handicap also. In Riemann integration, we have chosen to partition the domain AB with no reference to the function. Irrespective of what function we were dealing with, we always partition the domain. So it was, or P was So we had the advantage. The advantage was, in computing the area, you had this. See, each of this component in this sum, in getting the lower sum or the upper sum, we always had the advantage that we were working with the length of the interval xi to xi minus 1 multiplied by mi. Okay, and the length of the interval was defined of an interval, say xi to xi minus 1, or sorry, xi minus 1 to xi was defined as xi minus xi minus. So there was no problem about the length of the interval. The concept is very clear. Okay, right? So all this went through easily. So that had some limitations. So let us see how we overcome. Now what we do is we choose to subdivide the range into intervals. Okay. What we do is so we subdivide this into the range. So we modify our strategy. We subdivide the interval 0 to infinity. F into disjoint intervals. Okay. Now what one does is we look at this interval. Look at this interval and go for the pullback of this. Go for the pullback of this to the domain through the function. Okay. So what is the pullback? Look at the figure that I have drawn. Okay, so what we do is we now look at the set consider the set F inverse of L. That means the set of all x such that now this is a subset of And you see that the the each of these intervals that we have considered is called the closed open intervals that we have considered, which is taken as this to this. They get mapped to the following subsets. This is the portion that we end up with. According to the picture I have drawn, I mean, according to the figure I have drawn, if it is far more oscillatory, then you will get more intervals coming into it. Okay. Now you see, let us start approximating from below. So you see, on this set, what happens? On this set, f is approximated by the constant function yi minus 1. And an upper approximation is going to be, and from above by y, yi. Okay. So what do we get? We get the approximation, the lower approximation. This and over this, this. So you see that it is going to be, the approximation is going to be, that is yi minus 1 chi of f inverse y. The set that we are considering is f inverse of this one, this one, this one, this one in this example. This is what you call f inverse of okay. On this set, we take the function, the value of the approximating function as y elements. Now do it for every choice of I. Okay. If the function is unbounded, then there is going to be some place where you get infinite values also. Okay. Right? So that's the problem that you have. That's why we choose to avoid the upper approximation, but all lower approximations are certainly going to be bounded by the function yi minus 1. That's the maximum value that it takes on this interval. On this set. This is no more an interval. So what are the difficulties? Okay. That seems to be a good strategy. Okay. If it works. So let me just So what are the problems that you encounter? We know that f inverse of yi minus 1 yi need not be an interval. Need not be even need not be a finite union of disjoint intervals. Why I am saying this is this. Suppose this set is an interval, then you can talk about the length of that. And for this part, you can, write down the area enclosed as yi minus 1 times the length of this. The length of this, if it's an interval, then you see it is the length of that interval that you can use. But it may not be an interval. As you see here, there it's a union of 4 intervals as I have drawn here. Okay. Therefore, this is the area that you are talking about. This area, this area. So if it is a union of disjoint intervals, well, fine. You can still, take the length of the union of two disjoint intervals to be equal to the sum of the lengths of intervals. But that itself, we have not defined what you call the length of such sets so far. Maybe we will have to extend it, but that there's a way out. But you may not be surprised to see that this may not be a finite union of the joint intervals, because if your function is going to oscillate violently, then you see you may get and you may not get a finite disjoint set of intervals. Or let us go to this function. So consider the function fx equal to 1 for all x belonging to 0, 1 intersection the rationals, and 0 belonging to now this is what is called the Dirichlet function, or you can use this, write it as the characteristic function of 0, 1 the intersection Q. Consider this function. So it takes the value 1 at all rational points and takes the value 0 at all irrational points. So the range of this function consists of only just 2 points, namely 0 and 1. Okay. So that's where what we have. Now you see that to take any subinterval and work out this. You cannot draw the graph of this function. The graph of this function cannot be drawn. That is one problem. However, for any xy belonging to 0 to infinity, x less than y, or rather say a b belonging to this, a less than b, f inverse of ab is equal to empty if 0, 1 does not belong to f inverse of AB equal to 0 if 0 belongs to AB but 1 does not belong to AB. And f inverse of equal to no. If f inverse of AB, sorry, let's say consists of all Q if or 1 belongs to AB but 0 does not belong to now f inverse of AB equal to what? Complement means all irrationals. If mm, 0 belongs to AB but 1 does not belong to AB and it's equal to f inverse of AB equal to the whole of interval 0, 1 if both 0 and 1 belongs to for that matter you don't have to take any set, but we are interested only in intervals of this kind, right? You see, now what about the set that you have f inverse of AB? This is not an interval. This is also not an interval. So f inverse of AB need not be an interval. An interval. Nor an a union of a countable collection of therefore you see we cannot attribute a length to this easily. Attributed this set as the sum of that's a problem. So in these both these cases where if it contains only 0, if it contains only 1, I mean if it contains 0 but not 1, if it contains 1 but not 0, in both these cases you run into difficulties. Therefore, the type of step function that you define is it is easy to define the step function, but what do we say about the area enclosed between the the approximating step function and the ordinates and the interval AB, I mean interval 0, 1, that is difficult to make out. Okay, so that's a challenge. So in such cases, what we mean by length of a fingers of this is a problem. Okay? So that so we have to enlarge the scope of defining defining that is in when subsets like or okay. Okay, if that is possible, then how do you approximate? The approximation is then we can the approximation the integral of the approximation from below can be what? Chi, okay, chi q intersection 0 1 is going to be written as 0 sorry 1 into characteristic function of uh, say this will amount to this one. The fingers of 1 plus 0 times chi of f inverse of its complement. Okay, right? This is going to be the case. This is what it turns out to. Okay. This is the singleton 1, this is the singleton 0, and this is 1. Okay. The f inverse of singleton 1 is going to be all rationals on the interval 0 1. And this is what it turns out to. So this function, this is your, this turns out to be f itself. Okay. Therefore, what is the area enclosed? The area enclosed is going to be this. So we will have integral f equal to, in this case, 1 into length of f inverse of These are 0 times this, and under normal logic this is going to. Okay. So you see that you get an approximation which demands something. You have to talk about what is called the length of f inverse of 1, which turns out to be simply the all rational points on the interval 0. Okay. It is no more an interval, not even a countable union of disjoint intervals. Therefore, the whole concept has to be reversed. Okay. So this, in general, we are left with. So I'll stop here. In general, what we are left with is the task of talking about lengths of arbitrary sets in the domain. Attributing the concept of length to arbitrary sets of the interval A or even R. That is this is the domain of arbitrary sets. Arbitrary subsets of the interval, where AB is the domain of the function. Okay. So this is one of the major tasks that you have. Okay. And such that if such an arbitrary, an interval, say something like interval, then it should coincide with say CD. So that's our task. So we are now forced to enlarge the scope of what we call length to, if possible, for all subsets of the interval A of the domain. Okay, it's no more restricted to intervals. That is our task. Okay, and this leads to such a concept. Concept of this. Such a extension. Concept of what is called the measure of Z. We call that because length is a measure, measuring something, content of that interval, but it is defined only for intervals. You can immediately extend it to disjoint intervals by attributing the length of the union of disjoint intervals as the sum of the lengths of the intervals. But what happens if the set is not necessarily of that type? You may come across such situations. So we have to enlarge the scope of the concept of length to a larger collection of subsets, and that, when extended to our satisfaction, will be what you call the measure of the subset. And this is what is called, since the measure that you define coincides with the length whenever your subset is a interval. It's called the Lebesgue measure. Okay? So this is roughly the challenge that we have to undertake. It's not that it simply changes the partition from the domain to the range and then quickly get away with all those things, but you are challenged to do quite a lot of things to develop this theory, and that leads to the concept of what is called. Okay, now we will work on this idea, and just in my next lecture I will take up this scheme further. And then we make up a sort of strategy for defining the integral. Once we successfully see the path, then we will go about doing all those things rigorously. Okay? Thank you very much.